Hello everyone. Today we'll be going through how to solve A times A transpose or A transpose times A is symmetric using index notation. This will rely on understanding how indices work, knowing how summation works with matrices, and understanding indices a lot in general. So just here's a preview of the question. Exercise 6, matrix manipulation. So given that A is in Rm times n, show via manipulation using index notation that ATA is in Rn times n and is symmetric, while A in Rm times n show that using manipulation that AAT in Rm times m is symmetric. All right, so there's so many indices here. How do we figure out how to do this? So, knowing how to break this down can help you solve a lot of these kinds of questions. And we'll be going through the first part. So the first part is defining the matrix and then its components. So you have a matrix, let's say big A, and it has index I and j. So you can say that this is little aij for element wise. And from that, you'll see that if you get the index of the transpose, it's going to be flipped. So it's going to be AJI, where I is in 1 to m because it's the number of rows, and j is in from 1 to n, which is the number of columns. All right, so now that this is clear, let's look at how to do summation with a very simple case, and then we can build outwards more. So here's a relevant equation that you might see in a lot of places, which is AX. So AX is a matrix multiplied by, let's say, a vector instead of like a more complicated matrix. And we can look at how the indices work here. So looking at the right side over here, we'll see that if you write these indices out, this is going to be in this kind of format. You'll see that when you multiply everything that's what is it? It's going to be all of the column elements in each row times the row elements in each column for the next matrix. So over here you'll see it's A11x1 plus A12x2. Therefore, you can substitute these values or numbers with a summation and variables. And from this pattern, you'll see that, okay, the 1 is preserved across each column or each row. So this will be by itself, or just j. And then the k is going to be the number that changes as you add all of these terms together. And then at the end, you're going to be having a vector with all of these terms. So given that, now let's say x is wider, because let's make this like a 2 times 2 matrix for x. Then you can see that all this does is it actually just adds on more terms here. So one more term with the same pattern, except x is going to be x3 instead. x3 and x4. All right. So now that we know this, let me undo this. Okay, so now that we know this, we can simply put this into the process here and figure out how to just show that it's symmetric. Well, over here you have A transpose times A, which is going to be summation of A transpose times IK times element AKJ. And then because it's transpose from the top over here, you can see that it flips the bottom. So it flips it, so it becomes a KI. And since this is just a multiplication, you can rearrange this using commutative property. and then you get AJK times AKI. And then finally, you can change this back into the transpose. And from this, you can notice that it's basically the same thing, except now K is on the other side. And then J and I is also on the other side. Meaning that, first of all, I and J are functionally equivalent. And also, K is going to be flipped. So therefore, you can say that ATA, IJ is going to be the same as JI. So over here, what is it? Since we add up across all m's, then we are left with n vectors or n elements for the rows and columns. So then we can say that this is n times n in real space. You can do the same process for AATJ, IJ, and this is exactly the same process. Over here, we're going to do IK instead of KJ because the one in the middle, as you can see from here, is going to be the one that's going to be summing over. And then so you do the same process, and then you'll get that this is going to be in real space for m times m. So now what do you do if, let's say, there's 3 matrices? Well, you can do exactly the same process. So what you do is you nest these processes. And then from these nesting, you'll notice that there are different kinds of notations that later you can apply transforms to. And then you have these summations, which you can actually later flip around and then manipulate. But from this is the general idea. What you want to do is when you multiply matrices, you always multiply from left to right. So you're going to basically be doing this equals AAT times A. And then we're not going to be talking about if these multiplications are actually feasible, but this is just a process for showing how you can be able to get these later summation in notations for, let's say, for whatever more matrices you have. And that's pretty much it. That's the gist of this video. I hope you learn more about indexing and also how to show using indexing that the matrices are symmetric.